Last semester, you learned how to put rocks together. This semester, we're going to learn how to take them apart. We're going to talk about weathering of rocks, okay? And all rocks that are exposed on the surface are weathering away as the weather of the atmosphere hits them. Gases, liquids, solids, weathers them down and changes them into soil. Now, this is a very important process because a whole lot of what we eat comes out of soil, whether directly or indirectly. So if we didn't have soils, we wouldn't have a whole lot to eat. So therefore, we kind of have to understand how this weathering process forms. And also, a lot of our water is carried in rocks underground, and we drill down to it, pull the water out, and drink it. And so therefore, rocks really do play a very important role in our environment. Okay, and so what we're going to talk about now is how we start off with a rock and we change it into a soil, okay, or how we use it in an environmental application. And that's what this lab is about. So you're going to be kind of a review of last semester where you learned how to identify and classify rocks, but also think about it a little farther so that you can now take it into an environmental perspective. The first thing off when we talk about stability of rocks, in other words, how much do they resist weathering, how much do they weather? And the first and main aspect that you have to think about, main factor, is environment. Okay, what environment are they in? Obviously, you live up here in the Northeast and you got a lot of rain, it's a temperate climate, you got a lot of vegetation. Think about that as opposed to living out in the desert Southwest. If you lived in the desert Southwest, there isn't a lot of rain. It's hot, it's cold, so you got a lot of heating and cooling, more than we have here, not much rain, not much vegetation. And so therefore the environmental aspects, the weathering, is going to be completely different depending on where you are. And so what we have to think about then is that stability. And stability then we're going to take in terms of a specific environment. And when you do this lab, we're going to think about how stable or weatherable are rocks if they are up here in the northeastern United States, in New Jersey. Okay, and so that's what we're going to move to when we start doing this exercise. Now, there are two basic types of stability that go along with rocks. There is chemical stability, and there is mechanical or physical stability. And we're going to take those in two parts. We're going to start off with chemical stability. Okay, and clearly certain minerals are, and certain rocks, therefore, are more stable or less stable in our environment. Now, as we said, the first thing we got to think about is that the environment here in New Jersey is wet. Okay, so things that don't like wet tend not to be doing that well in this type of an area, as opposed to things that could be okay in a dry area. So if you went to the Bonneville Salt Flats, that stays pretty stable most of the year. But if you deal with any rock salt in the northeastern United States, and we remember how you can tell that apart, rock salt then is not going to be stable because it dissolves. Okay, and so therefore the chemical stability of minerals that will dissolve in water is not going to be very good in this part of the country, and so therefore the stability of salt is very low chemically in this area. Okay, another one, because we have such large amounts of vegetation in the area, we get a lot of rotting vegetation, and the rotting vegetation produces carbonic acid in most of our waters. Most of our waters are slightly acidic, okay? And so therefore, what does acid do to some minerals? It does to a lot of minerals. But what it will do is it will dissolve the minerals, okay? And it will dissolve the rocks away. So what you tried last semester when you were in your Planet Earth labs, and you would take a certain mineral and you would put acid on it, like so. Sometimes it would fizz, okay? And when it fizzed, that means we knew that it was calcite, right? Limestone, marble, all those calcite derivatives. But all that fizzing, what it really is happening is the acid is combining with the calcite to produce carbon dioxide, that's what gives you the bubbles, plus some salt, plus dissolved stuff. So the salt is carried along in the water, and you've gotten rid of now part of that rock. And so therefore, in the Northeast, specifically in New Jersey, acid in rocks dissolves carbonates. And so therefore they would have a very low stability in this area. And so there's kind of some extreme examples of chemical stability. If we want to look at other types of stability in chemically, we got to kind of think about how minerals are formed. They are happiest at the point of formation. Okay, once you get them away from their points of formation, they become unhappy or less stable. So, what does that bring us to? It brings us to Bowen's reaction series. Now, if you recall Bowen's reaction series from last semester, you had olivine at the top, and it went all the way down stepwise until you get to quartz. Quartz is real stable at the surface of the earth. Olivine is real unstable. Okay, olivine will tend to go to make clays. Whereas quartz, you find it all over your beaches, right? And so therefore, quartz is stable, feldspar is a little less stable, and you go up, and anything up above that becomes progressively less stable. The same goes for metamorphic rocks. Chlorite, which is a lower temperature index mineral, is more stable at the Earth's surface than is, say, sillimanite, okay, or starlite, or some of those high temperature minerals. And so therefore, the higher the temperature on the minerals, generally, the less stable it will be at the Earth's surface as opposed to the lower temperature minerals. And so therefore, you can go back in your book, you take your lab manual, this is going to be a review, and you look at those progressions of minerals, and then you can then judge whether these minerals, these rocks, are going to be relatively stable or relatively unstable, and therefore how they're going to fall apart in terms of chemistry. Next thing we have is mechanical stability, and that's the resistance to breaking down mechanically. Now there's a bunch of mechanical stabilities that we really can't measure too well in the lab. Things like how roots can dig into materials and break them apart, or cooling and freezing things, and we're not going to do that in the lab. However, one mechanical stability you can tell, and that is how resistant to scratching things are. Okay, if something is really resistant to scratching, resistant to abrasion, it'll last longer, whereas soft things tend not to last so long. So what you use then is Mohs hardness scale. For example, talc is not particularly mechanically resistant, okay, because it will erode away very easily with any kind of abrasion. Now, what causes this abrasion? It could be wind carrying along sand, and that would be a big thing out in the desert southwest, maybe not so much here, or it could be running water over things. That all is still mechanical stability. Those are things breaking stuff down mechanically. And so therefore what we could do is look at things in regard to Mohs hardness scale. So things that are very rich in quartz, quartzites for example, quartz is a very hard mineral, it's a 7 on the hardness scale, will tend to be resistant. Okay, anything hard will tend to be resistant, things that are soft will tend to be not resistant. So you have a chemical stability and a mechanical stability to consider when you look at these rocks. We talked about stability, turning things into soils, but there's also something else that rocks do. And a lot of times, the water that we have around here, that you're drinking water or water usage for personal use, comes out of a well. Okay, and so we have to think about what rocks might be able to carry the water and what won't. And so there's a difference between two rock types as to whether it will carry or won't. Now, most soils will carry water. But rock is another story. Some will and some won't. And so what you have then is two different basic types of rocks. A water-carrying rock, which is called an aquifer, okay, or a rock which will not carry water, which is called an aquiclude. Now there are some secondary features that can be put into aquicludes that will make them carry water, but in general, if we think only about the primary formation of the rock, they're either aquifers, carry water, and then can be used for drinking water and things like that. Unfortunately, they also carry pollutants. Or aquicludes, which don't carry anything, so no water goes through them. Now, how are you going to tell the difference between those in the lab? Well, the best way to do it is just dump some water on top of them. And so, for example, if we took this rock here, which, by the way, is a sandstone, and we put a little bit of water on top like so, and notice if I sit it right, a little bit came off. all of the water inside gets sucked up into the rock. So there's very little water left coming off of the rock besides what was sucked up into it. And that's why it gets so dark in color. Okay, and so therefore, this rock would be an aquifer. Now, if we then try, say, this, which is a mica schist, and put it as slow as we want to do it on here, no matter what we do, the water runs off of it. Okay, so therefore, the mica schist would make a good aquiclude. The sandstone makes a good aquifer. Siltstone, try that. We put a little bit on there. We can let it sit there for a long time. Okay, and notice that I've got the water sitting for a long period of time. And what's happening? It's not going anywhere. Okay, see, if I still dump it off, it still dumps off just as much as I put on in the first place. And so therefore, these are aquicludes. They make good aquicludes. Whereas this one, and you can see it's still soaking wet, still sucked into it, makes a good aquifer. Okay, so what you're going to do now is we are going to do the same type of exercise you did last semester in Planet Earth by identifying the rocks, but now we're going to put a little environmental spin on it. Otherwise, so you're going to have to then go back to your old book, and here's your classification schemes to be able to look things up. Go back, use your old DVDs, of course, so you can know exactly what's going on if you are rusty. And also, I have made a single page where it has all of the quick and dirty of all of the classification schemes for all the different rock types. So what we're going to do is, again, we're going to go through these unknowns, and we're going to figure out what each one of the unknowns is. Okay, and we're going to put it on a chart. You have a chart sitting in the back of your handout, and that's where we're going to put all of the information that we take from these samples. Now, the first thing we do is we're going to look at it the same way, and we again observe that there's a bunch of rounded grains on here. So this is definitely a sedimentary rock. Okay, and so we'll use the sedimentary rock system to classify it in here. If we look closely, we can see that being a sedimentary rock, you know, it's either going to be a clastic rock or it's going to be a precipitant. So if it's a carbonate, it will you'll get some reaction with HCl. So we can put a little HCl on it and check it out. And we see that the stuff just rolls off or absorbs. We don't have any reaction with HCl, so therefore it is a clastic rock. And so if we can then start filling out our form, we can see that in the first column it asks us whether it's igneous, metamorphic, or sedimentary, and we saw that it had rounded grains, so it's definitely sedimentary. In the second column it asks us then what the subdivision, and we said that it doesn't fizz, clearly has grains in it, so that makes it a clastic rock. Then we're going to determine what the rock type is. We go through our charts, figure out what we can say. This rock is mostly made out of quartz, all little rounded quartz grains. I'm going to call it a quartz sandstone. Purely review. Now we're going to start thinking about the environmental implications of a quartz sandstone. Okay, so the first thing we take a look at is whether it has a high, medium, or low chemical stability. Well, if we look at the page here that we show on the handout, we can see Bowen's reaction series. And on Bowen's reaction series, you can see that the minerals up on the high part are less stable. The minerals down on the low part are more stable. And the bottom one most mineral sitting on the more stable line is quartz. And in fact, since quartz is all over the place on the surface of the earth, it is one of the more stable minerals you can have. And so therefore, as far as chemical stability, we're going to say this is very stable. The next thing we got to think about is physical stability. And so again, we pull out our book, and notice how conveniently it turns right to the Mohs hardness scale. And you can see on Mohs hardness scale, we find quartz, which shows up at a number 7, okay, which is in the blue or hard group. And clearly, even this is the hardest, most common mineral there is. And so therefore, as far as physical stability goes, clearly this is going to be very stable. So we fill out the chart. Very stable. Last thing is the permeability porosity. Okay, and what we're going to do with that is the same thing I showed you how to do before. Is we take the rock sample, take a little bit of water and dump it right on top, and we're going to see what happens. And give it a little time to soak in. And if you look at this one, normally sandstone will be very absorbent. This one isn't that absorbent, probably because it has some cement holding the grains together, which tends to clog up the pore spaces. So what we have is that some of it is being absorbed and some of it is coming off. So it's not all going in, it's not all coming off. We've got a good, nice wet spot, but we also have a little that came off, and so therefore we're going to call this medium. Normally, in a sandstone, it would be very high. In this case, it's a cemented sandstone, so we'll call it medium. Okay, and therefore we have now filled out the chart. In addition to this chart, there are a bunch of questions. Okay, and the questions come into the second to the last page of your handout, and the questions refer specifically to the data that you've gathered on your samples. And for example, some of them will ask you which two of the samples that you would have looked at make the best aquifers. Well, you look for the ones with the highest porosity and permeability, and those would go in here. And that also asks you why. So you just got it. They have the highest porosity and permeability. Which would make the best aquicludes, okay? Again, look for things that don't have it, okay? Resistance to chemical weathering, resistance to physical weathering, building stones, things like that. And those are the questions. So you would take the data off of what you've already collected, and then you can answer the questions on how these rocks actually fit into their environment. And then you're finished.